Hello, my name is Kevin Rosas, and this is my Physics 2211 lab for oscillations. So the main purpose of this lab was to analyze the motion of a spring mass system with a mass oscillating in an arc. How did I do this? I used Tracker to track the observed positions in both the x and y directions, and then I used GlowScript as the computational model, which would predict the ideal model for this lab. And I did this to determine whether the computational model would actually follow the energy principles that we learned in class. And the final verdict is that the system's total energy remains at zero, which showcases the energy principle. So here's some fundamental principles. So first up, we got Newton's second law, which states that the system's changing momentum is proportional to the net force applied. And then we got the energy principle, which states that the change in energy equals the sum of the work done by the surroundings and the thermal energy exchanged with the surroundings. However, for this lab, we can state that there is no work done on the system and there is no thermal energy done on the system, which means that the sum of all the energies, or the change in energy, equals zero. Here on the right hand side, we have the position velocity update formula, which is pretty well known to us by now. Um, then we got the energy equations for a spring is 1 half kx squared, kinetic energy is 1 half mv squared, and then for potential gravitational energy, we got mgh. For the observed motion, we said that the object's mass was 0.402 kilograms. The stretched length of the spring was zero point 0.7 meters, which is measured from the top of the anchor point to the center of mass down here from the beginning of the frame. We said that the initial position was negative 0.118, comma negative 0.618, comma 0 meters, and that the initial velocity was 0 throughout as it is dropped from rest. And we solved that the period of the spring is 1.519 seconds. And in terms of finding k and the relaxed length L naught, in order to solve for k, we rearrange the period equation, which gets us 4 pi squared mass over t squared. And given that the mass is 0.402 kilograms and the period is 1.519 seconds, we can solve for k. And for L naught, given the final length of the spring, which is 0.7, we can subtract mg over k to get L naught. And in terms of the code, these beginning lines, I just plugged and chugged the values that I solved for in the previous slides. So here we got the mass of the ball, we got the position, the velocity, g, k of the spring constant k, and L naught. And in terms of the energies, I used the formula for the generic gravitational spring potential and added them all up to get the initial energy of the system. And here in this while loop, basically what's going on is that we're iterating through each time step and calculating the change in energy. So I first calculated the net force, from previous labs we know that the net force, and once we know the net force, we can find the velocity and then afterwards the position through iterative steps. And then using these quantities, we can then find the kinetic and potential energies of our system and ultimately change in energy at each time step. And in terms of the results, the GlowScript code produced two graphs, and here the two diagrams in blue in the left and right hand side, that shows what's going on in an ideal spring. So that's what GlowScript actually produced. And then the two red graphs show what actually went on in Tracker. And so what we could tell from these two graphs is that the two models towards the beginning tend to overlap, but then as time goes on, it starts deviating more and more. And the reason for this is that in reality, the system is not isolated from the surroundings. We have work being done on the system by, say, drag force that we don't include in our code. And another thing is human error, as I had to individually, for each frame, click on where the center of mass is, which becomes tedious and could lead to some errors by not putting the center of mass where the center of mass really is. So what does that all mean? Is the energy principle satisfied? Yes, it is satisfied. Since there's no external force doing work on the system change in the energy must be zero. And we see here on the right hand side that the sum of all the energies is constantly zero. And in terms of finding the oscillation periods, we found 3 periods within each of the x and y graphs, and then we averaged them up to find the average of the periods. So here, I found the average between these 2 points, these 2 points, and these 2 points. Summed them up, averaged them out, and I got a period of 1.66 seconds for the x direction. And then when I did the same thing for the y direction, I got a period of 1.52 seconds. And so what this does and what this shows is that different directions produce different deviations of the period, which ultimately affects the spring constant k and the graphs.